Hello, everyone. My name is Xing. I work for Huawei on OpenSDS. That's an open source project under Linux Foundation. I'm also a contributor in Kubernetes and CSI. So today we are going to do a deep dive on CNCF Storage Working Group. We're going to present our findings from the Storage Landscape white paper. And I want to thank Alex for preparing this slide deck for us. 各位早上好，我叫杨欣，我在华为工作。我也是 K8 社区还有 CSI 社区的贡献者。我们今天会讲一下我们在这个存储白皮书的里边的一些发现，跟大家分享一下。Here's my co-presenter, Quinton.
Good morning, everyone. Hi, yes, I'm Quinton. I also work for Huawei. I'm Technical Vice President of Cloud Computing there. I'm also on the CNCF CNCF Technical Oversight Committee that oversees all of the technical projects in the CNCF. And as my colleague mentioned, we're going to give you a little bit more detail about the work that we've been doing in the past year or so. In particular, a white paper that we're in the process of publishing. There's a good draft out there, so we'll take you through some of the detail of what's in there, invite you to participate, and hopefully have lots of time for questions and answers at the end. Do you want me to get started? Okay, so just to give you a little bit of background, so we decided a few months back, I guess around May, that we needed to clarify the terminology and just get everyone on the same page regarding storage in cloud native. It's a pretty complex topic. There are many different solutions out there. There are many different approaches to solving storage problems. And one of the problems we ran across was that not everyone had a good sense of the landscape, exactly, the different kinds of technologies out there, the pros and cons of different approaches, and they all have both positives and negatives. And also just using words, terminology, having a dictionary of things that people had a common understanding of. Not everyone fully appreciated the differences between various usages of some of the terms. So that was our main aim. Once we'd laid that groundwork, the next phase, I think, is to actually come up with some clear use cases, so show people how these things are practically being used in production in big systems around the world. And hopefully come up eventually with some recommendations about good practices and things that have been successful, things that have been failing or have seen failures and why, and what you can do to get the best experience out of cloud native storage. So these are the people, sort of the primary authors of the document, but we had many contributors from other companies as well. I don't want to get too stuck up there. I think one of the main areas that we really wanted to look at or the two main areas were, what are the different kinds of interfaces that you get to storage? Obviously, there's the data plane and there's the control plane and these kind of things. And even within each of those categories, there are many different subcategories. And it's important to understand the distinction between them, what they do, what they don't do, etc. And then the other area that we think is super important is just to understand the properties of storage systems, particularly cloud native ones. They're not always self-evident. I think in the old days where you had a honking big relational database in the corner and it gave you ACID transactions and the performance parameters were fairly well understood. In the world of cloud native storage, things get a whole lot more complicated. You have a bunch more trade-offs to make between consistency and performance and availability and durability. And some of the trade-offs that need to be made are pretty subtle. And so, there was a time where everybody said, oh, my big relational database doesn't scale and it's very expensive and we can't make it handle millions of users, so then we'll just go completely to the other end of the spectrum and we'll have these very NoSQL databases with data scattered all over the place and lots of horizontal scalability. And then people did that and they realized, whoa, hold on a second, this becomes pretty difficult to use. My data is no longer consistent. I write something and then somebody reads and they don't read the same stuff, and I've got suddenly the concept of a transaction where you have to do multiple reads and writes together across a distributed system becomes inordinately complex and my software doesn't work anymore, and then they sort of rewound back again. And so we're just trying to give a high-level view of where the industry has come from. I was involved quite well. I started the EC2 project at Amazon back in 2005, and I was quite deeply involved in the design of EBS and these kind of things. So I've seen over the years, and then I ran the ad serving systems at Google, which, as you can imagine, are probably one of the biggest systems in the world. Many millions of servers, very large amounts of data. And I've seen many different failure modes. So hopefully we can give a little bit of perspective over time as to where the strengths and weaknesses are. The primary attributes that we really think are worth having a clear understanding of are availability. How available does your storage system need to be? What happens if it's not available? In some cases, that's catastrophic. In other cases, it's much less catastrophic. How does this thing scale? One of the failure modes I've seen in many organizations is everybody thinks that they run, Google search, and they need, this enormous scalability, and that scalability comes at a cost, whether it's operational cost or other forms of cost. It's very important to not pretend that you're going to have 1 billion users tomorrow, because, relatively few services do actually have 1 billion users. And even when they do, it typically takes a while to get there. You don't have to architect your brand new system to be able to handle 1 billion users from day one, because it often doesn't happen. Also don't, architect it to have 3 users, but somewhere in between there is a sweet spot. Performance is, again, very important. Some people have in the past, gone from, we spoke about the relational database model to all the way at the other end of the spectrum, and then they suddenly realized, ooh, my 10 millisecond latency updates now became 500 millisecond updates, and when you have 50 of those in loading a web page, suddenly things don't look so good anymore. So it's very important to understand the different characteristics of performance. So there's latency, there's throughput, there's many different dimensions that one needs to be aware of there, and we're going to dive into that a little bit shortly. Consistency, as I mentioned, is a very thorny topic. For starters, the very word consistency means completely different things to different people, and even down to, many of you have probably heard of the CAP theorem. Consistency, availability, and partition tolerance is what CAP stands for, and it's a pretty fundamental concept in distributed systems in general, and it applies to storage as well. And then almost everyone who's heard of storage of any sort will have heard of ACID, atomicity, consistency, idempotency, isolation, and durability. And people think, oh, there's a C in there as well. It also stands for consistency. Turns out it means a completely different thing than the consistency in the CAP theorem. And if you don't understand that, you can get yourself very confused. So hopefully we can help you understand some of those things. Right. So just to dive a little further into those properties, when we talk about availability, we're talking about a bunch of different things. Failover, how do these things fail over? Are they available while they're failing over? Is it acceptable to have a very brief, unavailability period while automatic failover happens? Maybe from in a quorum system, you often have a leader election that might take place, and that might take a few seconds, and then between, during those 2 seconds or a few seconds, you might have a small outage, which is very different than having to wake up an engineer in the middle of the night to go and figure out what's wrong and do a failover. So being clear on the distinction there. How do you make sure that you can move access between different nodes? If you have a node failure, for example, in a system, how do you migrate everyone to know that the data that used to be on node A is now on node Z because there was a hardware failure of some sort, either a network or a computing storage node failure? And then what do you do about data protection? If things become unavailable, do you end up with corrupted data? How do you make sure that if you read a piece of corrupted data that happened during a failure, can you identify it? Can you fix it? These kinds of things. Scalability, as I mentioned, has various different dimensions. So the one obvious one is how many clients can you handle? In some applications, You don't necessarily have a large number of clients. You might have 50 or 100 or even 1,000 instances of a microservice that all access a database. In other cases, you might have millions of users directly accessing a data store. And the scalability aspects of those two are very, very different, obviously. Operational scalability, so if you have any degree of manual intervention or human intervention involved in the operations of these things, does that scale with the size of your data set? Does that scale with the number of clients? Do you have, client software that needs to be updated on Android phones, for example, and what does that look like? Obviously, another area of scalability is the throughput of this thing, either in terms of the number of transactions, number of updates, number of reads, number of bytes of data. And the different kinds of storage technologies have very, very different properties in this regard. So you can imagine if you're storing stuff in S3, you get a very good throughput on some of those axes, but very bad throughput on other axes like latency. And latency and falls under performance as well. Want to see if there's much more. So I've spoken a fair amount about performance. I think we'll dive into that a little bit more in a moment. Consistency, I think I've also spoken about. There are a whole bunch of subtleties there about the delay between, once you commit a write to the data store, at what point does everybody read that write? Do you read that write immediately? If you have another transaction, does some other user read the same data that you just wrote? What if they're writing at the same time? All of these things come into play. And then in some cases, there is a necessity to actually consider a transaction to be, persisted when it may not actually be fully durably persisted. But in some cases, you can get away with that if you spread it in the memory of multiple nodes before you put it on disk. You can consider that it's durable. And as long as at some point shortly thereafter it ends up being put onto durable storage, non-volatile storage. But that, there are risks associated with that, and as opposed to the risk of having very low throughput because you have a spike of data and everything has to be persisted onto possibly, spinning disks in order to get that to happen. And durability is, again, an area that has many different dimensions to it. How do you make sure that your data is encrypted at rest, possibly? What form of redundancy do you have? How many failures can you handle before you actually lose data? What happens if things, degrade over time? Is that data still valid and consistent after a period of time when it might have links to other data that doesn't exist anymore, etc. Okay, and I think somewhere around about here, I'm going to hand over to my colleague Xing, who can take over from me.
Thanks, Quinton. So, storage solutions can be deployed in many different ways. It can be deployed as a hardware solution in a data center, but that could limit its portability. And it could be deployed as software components on commodity hardware. That means it could be more platform agnostic. And the cloud providers also provide storage services in the cloud environments. So this diagram shows workloads consume storage through a data access interface. And the data access interface here have two categories. One is volumes, the other is application API. And volumes here include both block and file system. So the COs supports volume interfaces directly. Kubernetes has two volume modes. First one is the file system mode, and then the other one is the block mode. File system mode has been supported since the very beginning, and that allowed the file system to be consumed by workload directly. Although underneath, it could be either file system or block systems. And block mode was added later. It is still in alpha. That allows a raw block device to be consumed by workloads. So that is actually very important for some database applications such as MongoDB, Cassandra, SAP, that requires consistent I/O performance and low latency. So block storage stores data in blocks, and each block has an address that can be used to access data. Then block systems can be local, remote, or distributed. And file systems persist data in files and directories. And file systems usually use a block device to persist data underneath. And file system has access control, concurrency control, and locking, name and directory structure that makes it much easier to be used directly by applications compared to block. File system, shared file system can be accessed simultaneously by multiple nodes. File system can be local, remote, or distributed. This is regardless of the block storage underneath. And for application APIs, that includes object stores, key value stores, and databases. So object stores uses a API to store and retrieve object or blob. And that usually is an HTTP interface. Object store usually uses a distributed architecture, and that is optimized for capacity, durability, and scalability. It could also have a higher latency because of that, but it could also provide high throughput through parallel access from multiple clients. And key value pairs using API to store and retrieve values based on a key from the data source. Key value stores usually is implemented with strong consistency, so that makes it easy to use by many distributed systems to store state and configuration data. Databases is out of scope for this version of the paper, so I will skip that. There are many storage layers that could impact the attributes of a storage system. So I will go over those layers. There are layers that are overlaid on top of the data access interface as part of the orchestration that would have an impact on the attributes of the storage systems. So for example, instead of directly accessing resources, a hypervisor could provide access to the resources through some kind of mapping, some kind of pooling, and resource management that could add some overhead on access. And storage topology is another layer that could affect the attributes of the storage systems. So this describes the different arrangements of compute and storage, and also the data link between them. So for centralized topology, usually you have a small number of nodes tightly coupled with each other, and usually many vendor-specific hardware storage solution uses this, and it can be scaled up, and it is more consistent with lower latency compared to distributed systems. And then this usually is used in many block-based systems. And the distributed topology usually has a focus on software. So you have software components deployed on commodity hardware. And it usually uses a shared nothing architecture, but you need to synchronize across nodes over the network. That can be scaled horizontally by adding more nodes and more clients. But that could also add the complexity to operate. And the sharding. So sharding is used by many database applications to partition the data set. That can be scaled horizontally, but it could also have added operation complexity. And the other topology is hyperconverged. So this topology, usually you would have a compute and storage resources deployed together on the same node. Usually you would have a few nodes clustered together to form a pool. Usually it uses the software storage components on commodity compute nodes. So this has the similar attributes as the distributed systems. It is very flexible because you could scale your storage nodes together with your compute nodes. But the downside is this tight coupling also means any failure on a node could fail your storage systems. And many storage systems also have a data protection layer through redundancy. Here we refer to RAID, erasure coding, and replicas. So RAID uses striping, mirroring, and parity together. So striping, you basically spread your data across. You basically spread your data across 2 or more disks, and that could add the performance. And for mirroring, you have a duplicate set of data across 2 disks that could use more space. And for parity, you basically distribute a data set across a number of disks, and then that is grouped together. And then for each unit of data, usually a block, you use an algorithm to generate a set of parity for added redundancy. So striping, mirroring, and parity are usually used together in different combinations for a RAID configuration. Usually RAID is used in the same node, but it can also be used in distributed systems across several nodes. And erasure coding, basically that split data sets in multiple segments, and each segment is encoded, and then it is stored with a configurable number of redundant parity sets. So that would have added redundancy and durability. Erasure coding is used in many distributed systems. It is the main building block of the many object stores. But that could also have the computation overhead and also added latency. And then the replicas, basically you have mirrored data sets across multiple servers and nodes. So a replica is a complete copy of the data set. So that has a lower computational overhead and lower latency. And many storage systems also have data services in addition to the core storage functions. So here we refer to replication, snapshots and clones, and encryption. Replication refers to remote replication. So you'd have a primary and secondary storage, and usually across 2 or more sites. And replication could be synchronous or asynchronous mode. In the synchronous mode, that means more consistency, but it's also limited to the distance. And for asynchronous mode, that is usually used for long-distance replication. That also requires adequate bandwidth to make sure the data is transferred to the remote side in an acceptable amount of time. Replication usually have requirements for RTO and RPO. A snapshot is a point-in-time copy of the data. In snapshot, usually the copy on write technology is used. That is very space efficient because you only need to save the delta between the original and the new data on that snapshot. Snapshot may or may not be dependent on the original data depending on the storage systems. And a clone is a full copy of the data set, and clone is not dependent on the original data. So the snapshot is usually read-only, and clone is usually read-write copy. and they can be used to restore data. Encryption is another thing that many storage systems use to protect the data, and encryption can be applied to data on rest and data in transit. And ultimately, we would have a physical layer. The storage systems have to persist the data on some physical layer, usually a non-volatile layer, and that would affect the overall performance and durability of the data. So we have traditional spinning disks that has low cost. And then we have SSD that can be used with the traditional interface, SATA, SAS, and SCSI. SSD stores data in non-volatile memory, so it's better performed, so it has a lower latency, but the throughput in this case is still limited by the transport. NVMe is a new transport that is designed for flash, so it is fast, so that can achieve much lower latency and much higher throughput. We talk about the orchestration, the management interfaces. Here we have the workload consume storage through a data access interface that is showing in C here. And then for the storage system, it has two ways to interact with the orchestration, container orchestration systems. Here we have A and B. This darker green box, container plane, control plane interface, that refers to the volume interfaces supported by the COs. So that includes CSI, the Docker volume interface, and the Flex volume and Kubernetes native driver interfaces. And that is usually more focused on the provisioning side, dynamic or static provisioning. And then you can see that there is also this orange box here that says frameworks and tools. So that is actually an extension of this control plane interfaces in darker green. So that could provide additional functionalities. In addition to the provisioning, it could have support for discovery, automation, additional data services such as disaster recovery, data protection, data migration, data lifecycle management, monitoring, analytics, performance tuning, and so on. And examples of the frameworks and tools here include projects such as Rook, OpenSTS, Rexray, and HapShare.org, and there are more. So going back to this control plane interfaces in this darker green box. So for the native interfaces, we have the Kubernetes entry drivers. So that supports both block and file systems. So that supports create and delete volume, attach and detach, mount and unmount, and expand volume interfaces. And we have the Docker volume driver interface that has support for create, delete volume, and mount and unmount operations. And for external interfaces, we have Flex volume. Flex volume supports attach and detach, mount and unmount. So Flex volume does not have interfaces for provisioning, but you can have a dynamic provisioner and have that used together with your Flex volume driver. Because right now this SIG storage wants to move towards the CSI, so new features will not be added to Flex volumes, and the entry drivers, new features will be added to CSI. And CSI container storage interface, that is an industry standard to define a set of storage interfaces so that a vendor can write just one plugin and have it work across a range of container orchestration systems. So that includes Kubernetes, Docker, Mesos, and Cloud Foundry. So CSI has 3 gRPC services: identity, controller, and node. So for the identity service, it has information and the capabilities of a plugin. And the controller service supports create, delete volume, attach and detach, create, delete snapshot. And for the node service, it supports mount and unmount operations. And also expand volume support is coming. That would be for both controller and node services. So right now, we are actually in the middle of trying to get CSI GA. So 1.0 release is coming soon. We do have implementation for CSI from Kubernetes side and also Mesos and Cloud Foundry. I think Docker is also working on a driver. There are also application APIs. So the controller, the container orchestration system do not have direct interface to support the application APIs. Yeah, okay. But there are some, the frameworks and tools do have support for that. I think there are some examples of that, including like, for example, Rook, it has support for Minium Object Store and Cockroach databases. And Vitas has support for MySQL databases. And Rexray and OpenSTS also have support for Object Store. Okay, so the next steps, we want to find out what is missing from this white paper. We want to finish the paper by KubeCon Seattle. And we also want to get some feedback from audience on what we should do in this working group. Some other sessions, I think some happened yesterday, some will be today. Okay, so yeah, that's our presentation. We want to see if there are any questions.
Thank you. And I want to ask about snapshot feature of the Kubernetes. I've been actually digging around about the snapshot feature for some time now, and I think there is something called FS freeze that pops a lot. So if the file system is not in a consistent state, it will be maybe not feasible for doing a snapshot. I've personally using RBD and they all say that's true. So I think that's what Rook use. Thank you.
Unfortunately, we're starting to run out of time, and that's a sort of a deep dive area. So I think we should maybe take that offline after the talk and talk more about that. Any other questions?
Okay. You want that one later? Or?
I just thought we might want to.
Sure. Okay, so I can follow up with you. Are there other questions? Okay, so while waiting, I can answer your question. So basically, right now, the snapshot feature, we don't have the freeze functions integrated with it, but we are actually working on the application consistency. This is something that we're actually currently working on. We're trying to add some hooks so that you can add those actions like pre-action and post-action. Yeah. Any other questions?
Now all the data, all the volume will mount it in the host. So is there any way to let the container to direct access the data without mount any volume in the host? And keep the data out from the infrastructure maintainer.
I don't think, I haven't seen that type of possibility right now. I think you do have to mount it somehow. It could be block device, so not file system and then block. Yes, block device is possible now, yes. Mm-hmm, yeah. Mm-hmm. I'm not sure about that. I'm not sure about that part. I think right now you do need to make it accessible by the host at least. I don't think it's possible that you without that. Yeah.